Hey everyone. So we are going to talk today about our sort of journey from using Postgres DB to ScyllaDB for our next generation query engine. So I'm Dan Harris, and I'm here with my colleague Sebastian Verkois. We're software engineers at Coralogix working on our next generation distributed query engine. So we're going to give you a little bit of background about the query engine itself and the Metastore, which is what we are using ScyllaDB for, how we're using ScyllaDB to implement that, and then a little bit of conclusion about some of the lessons learned we've had in this migration. All right, so we're working on a product called Data Prime Query Engine. And so this is a custom distributed query engine for a proprietary query language we've developed here at Coralogix called Data Prime that's designed to efficiently query arbitrary semi-structured data. And the underlying data is going to be stored in object storage, so S3 or some other object storage system, and stored in a specialized Parquet format that we've sort of designed in-house. And we sort of designed this platform initially with just basically as a stateless query engine on top of the underlying object storage. But we sort of quickly found out that the cost of reading Parquet metadata during query execution is a large percentage of the query time. And since latency is important, we sort of developed what we call the Metastore. So this is essentially a way to take Parquet metadata that we need to execute a large query and putting it in a faster storage system that we can query quickly so that we can sort of reduce the amount of time that we spend dealing with Parquet metadata and can sort of scan the actual data faster. So we use this for a couple of things. One, we store the Parquet metadata in a sort of decomposed form in the Metastore. And then we also have a sort of what we call a sort of block listing system, so that for any given query, we can basically know exactly which files that we need to scan to execute the query. And then on top of that, we also need a sort of transactional commit log so that we can transactionally add, update, and replace existing data in the underlying object storage. So we have a couple sort of core requirements here. One is like low latency, right? Part of the point of this was to limit the amount of time we spend dealing with metadata. So that was sort of the first most important requirement. It needs to be scalable, both in terms of how much we can scale up the read and write capacity, and also storage, how we can scale the sort of underlying storage. So as an example, for just one of our larger customers, they write about 2,000 Parquet files per hour, about 50,000 per day. That's 15 terabytes of Parquet data per day, and 20 gigabytes of just Parquet metadata. And that's one day for one customer. So just storing the metadata is something that needs to be extremely scalable. And we sort of started this, an initial implementation on top of Postgres, understanding at the time that a non-distributed engine would not really be sufficient for the long run. So there's a couple sort of key things that we store in the Metastore. So the first thing is what we call blocks. So this is basically one row group and one Parquet file. And it's basically just some high-level metadata about that row group. So the URL and object storage for that file, the row group index of the block, some very light metadata about what's in that file, like the minimum and maximum timestamp for records in the file and total size and number of rows. And then additionally, we want to store a way, we want to sort of provide from the Metastore a way to sort of prune what we actually need to read based off something that we can do when we're listing the underlying blocks. A cheap-ish way to do that is to use Bloom filters. So essentially, we want to support something like full text search. So we basically, when we're ingesting these files into our system, we can sort of build a Bloom filter for all the distinct tokens that we find in the file. And then based off a particular query, we can use those Bloom filters to actually prune the data that we need to scan to begin with. We need to put this in storage somewhere so that it's sort of quickly readable. So we sort of break, we use a basic block split Bloom filter setup where basically you have the Bloom filter broken into 32 byte blocks. And then we can sort of store those independently so that we don't need to read the entire Bloom filter during query time. And then finally, we store the column metadata. So this is basically for each column in the Parquet file, we grab just that chunk of metadata and we store that in the Metastore. So the files that we're writing are quite wide, sometimes as many as 20,000 columns. So by reading only the metadata that we need to, we can really reduce the amount of I/O we need to do on any given query. All right, so I'm going to hand it over to Sebastian, who's going to sort of tell you a little bit of how we implemented this on top of ScyllaDB.
So let's start with how we modeled the blocks. So what you see here is an example of a block URL. You can see the blue part is the customer's top level bucket. And inside the bucket, things are partitioned by hour. So the question is, what should the primary key be in this case? Well, we could use the table URL, but the problem there is that some customers have way more Parquet files than other customers. So, we want to keep things balanced. And, that's why we have decided to not go for the table URL. We could use the block URL in the row group, which uniquely defines a block. But it would be very hard to, list all the blocks for a given day, because the timestamp is basically not in the key here. We could then use table URL an hour, and that works because, if you have 24 hours to query, you can just query it quite easily. We made one addition, like we added the segmentation key, so we can easily find a given block in an hour. So if you want to delete something, that's also pretty easy. Let's move on to something more interesting, the Bloom filters. So as Dan mentioned, we need to verify that certain bits are set. The question is, how do you do that? Scylla doesn't have anything like custom for that we can easily use. So the solution is to read the Bloom filters and process them in the application. The problem here is that we have sometimes 50,000 blocks per day for a customer, times 262 kilobytes, which is the size of one Bloom filter. And we have 12 gigabytes of data, which is just too much to pull back into the application for one query. So what we do is we chunk the Bloom filter because, as Dan also mentioned, we don't need the whole Bloom filter. We just need like part of them, depending on the tokens. So we chunk them, we split them into rows, and then per token that we need to find, we basically only need to read 1.6 megabytes, which is way more doable. Then another question, what should the primary key be? Well, we could say like we're gonna group, because one block has one Bloom filter. So you use the block identifier as the primary key, and then use the chunk index as the other key. But, and that works, you have 8,192 chunks times 32 bytes is 262 kilobytes. So pretty evenly spread. per partition. It's also easy to insert. Every Bloom filter is in the same partition, so you can just do a single batch query. The problem is, we're reading the blocks, so sometimes we're reading 50,000 blocks, and you need to know the ID of the identifier of the block before you can, read the Bloom filter. So if you're doing a listing query for 24 hours, of course you can pipeline it. As soon as blocks come in, you can start reading Bloom filters, but you still have this dependency, which is a bit annoying. Also, you have to access really a lot of partitions. Like if you have 50,000 blocks, you have 50,000 Bloom filter partitions that you have to access. And, even if Scylla is super fast, it's still going to be hard to do that in less than a second. So we decided for something else. We basically, same as with the blocks, we partition by the table URL, the hour, and we add the index to the partition key. And the trick there is because in our application, we know we need the 5th token, we need the 10th token, we need the nth token. So it's pretty fast to just we read the whole partition basically this way for an entire hour. And, that gives us 24 hours times 5 tokens is 120 partitions. Compared to 50,000 partitions, that's a lot better. We also don't have a dependency on blocks anymore, so we don't need to have the block ID before we read the Bloom filter, which is also nice. We can just do both things in parallel, and then at the end we can match them together. But there are also some downsides, because now we have to insert our single Bloom filter in 8,192 different partitions. Also, if you want to delete one, we have to access a lot of partitions. But reading is more important for us than writing. These queries have to be fast, so we really it's very important. Also, in the future we might want to investigate a bit more of an optimal chunking. Now we split into 8,000 plus rows. Maybe we can split into 1,000 rows and fetch a bit too much data into our application, and it will still be fine probably, and we'll definitely speed up our inserts. But what we really would like to do in the future is, just move the work to Scylla basically, and start using UDFs, so user-defined functions. We already have everything written in Rust, so we can, it would be really nice if we can start using the UDFs, and basically, we don't have to send anything back to the application anymore. And, that gives us a bit more leeway to play with the chunking that we would need to do. Also, just some advice. I wasn't used to, working with Scylla or Cassandra, but, it looks a bit like SQL. I know it says no SQL, but still, you have this ID that is still SQL. And so one day I figured out, after we were already importing data for a day, that I messed up min and max, and I thought, oh, okay, how am I going to fix this? And I thought, maybe I can rename the columns to something else, and then somehow make it work again. The problem is you cannot rename columns if they're not the clustering key. So, okay, I had to find something else. Thought maybe I'll add new columns and do an update blocks set to the old value. Unfortunately, this also doesn't work. It works in normal SQL and Postgres, but couldn't here. So we ended up truncating the table and starting over again, because that seemed less work than just, writing migration code at that point. I don't know what the advice is here. Don't write any bugs, but that's not easy, of course. So just be careful. Modeling and writing the code is one thing. So we use the ScyllaDB, use a lot of ScyllaDB components. We've written our code in Rust using the ScyllaDB Rust driver. But one of the main things attracting us to Scylla was also the operator for Kubernetes. We're pretty big Kubernetes users, and having something that's easy to set up was definitely a priority for us. And we also use ScyllaDB monitoring, the manager. So, these components really helped us to make it production ready. And from deciding, we might want to use Scylla, we were basically more or less production ready in 2 months, which is quite nice. Hardware, cost is very important to us because the whole point of this project is to provide a low-cost alternative for customers to query their data, their logs data, their metrics. And so currently we're, I think, using the absolute minimum that is sufficient for us. So we have a 3-node cluster with 8 CPU, 32 gigs of memory. We're on AWS, so we're able to use ARM Graviton, which is nice because it saves some cost. Then a more controversial decision is that we're using EBS volumes at GP3. Not spectacular numbers, I would say. But yeah, we're trying to make it work this way, and we'll see how long we can manage. So for the block listing, maybe some numbers. So we have about 4 to 5 terabytes on each node. Currently, we're only doing this for one customer. We're doing about 10,000 writes per second, and the latency is lower than 1 millisecond, which is nice. For block listing, it very much depends on the customer and the query and how long it is. If it's like 1 hour, so about 2,000 Parquet files, and we're using Bloom filters, it's less than 20 milliseconds. For 50,000 files, it's less than 500 milliseconds latency. But bear in mind that we also do, the checking of the bits and stuff, and we could probably optimize it further. But for 50,000 Parquet files, less than 500 milliseconds is just good enough for us because the actual query that comes afterwards will be quite a bit longer. So, but I'm sure there's room for improvement there. Column metadata, we have a bit of an issue there because the P50 is really good, but we do notice that there's a bit of a high tail latency, and the problem is there that if we have 50,000 Parquet files, our executors are fetching all of these in parallel, and we just have a very large amount of concurrent queries, and we're not using the best disks, so we assume that is what's causing the issue for us.
All right, thanks, Sebastian. All right, so what are the lessons learned here? So, I think the biggest difference between ScyllaDB and using other DBMS systems is that you really have to think very carefully about how you're partitioning and partition sizes. So we went through quite a few iterations, as Sebastian mentioned, figuring out what our partition and clustering keys were, and it's really important to performance. And then, you have to think again about your read-write patterns, right? So are you read heavy, write heavy? Do you need a mixed workload of lots of writes and reads? In our case, we are quite write heavy because we are constantly ingesting data, but we also need to prioritize the reads because read latency is very, very important to our product and customers. And write latency is we have a lot more leeway there. And we're quite happy with the fact that we could get the block listing in and sort of get P99 latency there under 500 milliseconds while you're doing basically Bloom filtering with across tens of thousands of individual blocks. But for reading the column metadata, it's been a bit more mixed, right? So it's when the P50 latency is fantastic, right? Being able to do that in less than 5 milliseconds, but the high tail latency has been sort of problematic. And then along those lines, we were sort of warned try not to use EBS, but we didn't listen, and we probably should have. So, if you're considering using Scylla, it would probably be a good idea to look at sort of instances that have local SSDs instead of trying to use EBS volumes. Cool. All right, thanks. So our contact information is there. If you have any questions or like to reach out, please just drop us a line sometime. Thanks.